Welcome again. So remember, this is the idea that we've been keeping for a while is that under a region we can divide it into infinitely many n rectangles. Let n go to infinity means delta x means the length of the base starts going towards zero. So those are two equivalent statements. And furthermore, now we just said that if we take the limit of a summation of infinitely many rectangles, we actually get this new notation right here. And this new notation, we're going to say that that is our integral. And furthermore, it's not only an indefinite integral, this number here and this number here make it a definite integral. You definitely know where you're going from where to where. The other one is indefinitely. You don't know from where to where because you get an indefinite number of family functions. And what do we get with the definite integral? We get a number. This number for now, it represents the area bounded by a function and the x-axis and the vertical lines A and the vertical lines B. And it's saying f of x is said to be integral. A function is said to be integrable on a closed interval. Remember, this becomes really important notation. Why does it need to be closed interval? Because it needs to go from a point A to a point B. That's why it needs to be a closed interval. The limit, once you take the limit, it's called the definite integral. It's saying that once you take the limit of this, it's actually the same thing as the definite integral from a to b. So we have the integral from a to b of f of x dx. This is where you're starting, this is where you're ending, taking your area, all right? And this will give you a numerical value. Nice number. That's what the definite integral will give you. So now, continuity implies integrability. We apply by that. So if we say that a function is integrable, that means that we can take the area under that function's curve, right? So if it looks like this, we can take the area from a to b. We say the function f of x is integrable from a to b. If I have a function, let's say a constant function y equals c. Well, the area from 0 to, let's say, b, a is 0. Oh, I can find the value. It is a number. So we say that this function is integrable from a to b. Look at this beauty. We'll learn this later. But we say that my function is integrable from a to b, that I can find area under and then below. D of x is equal to a number again. Remember, every time that I'm taking integrals from a to b, integrals from a to b is giving me a number. So if I have a function that is continuous, meaning that there's no breaks, is this continuous? Yes, it is continuous. Can I take the area from a to b? Yes, I can take the area from a to b. So I can say that f of x is integrable from a to b. Now, do you remember continuity now implies that a function is integrable? So continuity implies integrability. Continuity also implies what? Or does it imply? That's a question that I want you to understand. In terms of derivatives, what does continuity implies of my function? Does continuity implies that differentiation? Or does differentiation implies continuity? Which one is it? Stop here, pause, go back to your notes. You need that knowledge to move on. All right. So here, let me pause it myself as well. No, let me continue. Why? Because of what I just explained. We can take the area under. Now, let's establish this. Because f is continuous, then f is also integrable, as I mentioned earlier, which means that I can find the area from a point A to B. So if f is continuous on a closed interval A to B, then f is integrable on the closed interval A to B. That is this notation. This number exists. This is a number. This is a definite integral, and it is a numerical value. What does this numerical value represent right now? It just represents the area under the curve. Is that number that you would have gotten by taking the limit of that summation from I equals 1 to n of the right endpoint, blah, 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 blah. That is what this number is now. All right, so what is the difference between definite and definite integral? At this point, you should be able to establish what is the difference between the two. A really simple one is just going to be that an indefinite integral, it gives you a family of functions. If you take the integral of little f of x, remember what we get? We get f capital of x plus the constant of integration. This constant integration, this is the general form. This is the general solution. General solution. Once you substitute an initial condition x f of x, then you get the value of c. Then you get the particular. But what does an indefinite integral gives you? Nothing but just a family of functions. What does the definite integral gives you? It gives you numbers. Numbers. What are these numbers? Numbers. For now, these numbers represents the area under the curve from A to B, whatever my function may look like. That is what we have so far. So here's the theorem, and this theorem I'm gonna save it for the next video, video 3. Yay, thank you.